And, hey Meg, hope you're doing well. Am I the only one saying hi to Meg?
Hi, Meg!
Don't want you to feel lonely, Meg. Hope you feel better. Wow. Well, in any event, you know what? We began 16.7 actually yesterday, just as a brief introduction. I'd like to quickly summarize what we talked about. Surface integrals. What we're going to do is see that just like from the previous section, we can have a solid, a surface that's defined with a vector function, parametrically defined. And of course, we could have patches on that. And of course, you can think about computing area. But what is happening here with many applications to the sciences is that we will be looking now at a surface. And what will happen is we will take a random point on that little patch and evaluate a function with that ordered triple on that patch. The x comma y comma z is on the patch. So like we were saying yesterday, in the past, you would evaluate functions. Last year, we built rectangles just in an XY plane. This year, we were dealing with sneaking in double integrals and triple integrals. We would first say, hey, let's assign perhaps for a double integral. We'd look at a little tiny rectangle, subrectangle, an x by y rectangle, and pick a random point in there and assign a height. What you're doing right now is you're applying that function. Imagine that we're building a rectangular prism, if you would, right off of that solid. And my goodness, that will have some direct applications to electricity and magnetism very, very soon. So notice what we've highlighted in these boxes. We're saying we're going to define a surface integral to be a function evaluated at a point multiplied to that little area patch. So when we get down to the official definition, you can see the S written below this double integral. It's saying this is a surface integral, working it out the way we just spoke of. And we will have a function that we're going to be evaluating. We're going to plug in our r, comma, u, comma, v. Whatever x, y, and z are defined parametrically, we plug that into the function as well. And then we will multiply that by RU cross RV and its magnitude. Now, we began example 1 yesterday just because we had already done a problem so incredibly close on the notes from 16.5, or I should say from the notes of 16.6. I miswrote that. But on the previous day's notes, we actually worked out in spherical coordinates what x, y, and z were. Here for this problem, for example 1, we're going to have a unit sphere with a radius of 1. So you can see x, y, and z on right below the typewritten problem here. We've got x, y, and z defined in spherical coordinates with a radius of 1. But we already saw as a shortcut, the author did this too, that the length of that cross product was just a squared sine of phi. So we could say it's just 1 times the sine of phi. And my goodness, right now, inside this integral, you can see that we have x squared. X squared, of course, is a very different function from the solid, from that surface, I should say. And even though that's the case, our function is going to be touching and be defined on that little patch. So the parametrization that we have for the surface will be applied to the function as well. So x squared, we already had x was equal to sine of phi, cosine of theta. We could put that in there. And then very, very quickly, I stopped right here, but I just want to hopefully state the obvious. Cleaning this up, we've got sine squared of phi and another sine of phi. This is sine cubed of phi. And then we'd have cosine squared of theta. but our dA is dependent on our parameters, so we could have d phi and d theta. And our sphere, what do you think our boundaries are for phi if we've got a full sphere here? We're going to go from what to what? 0 to pi, absolutely. How about for theta? We'll go from 0 to 2 pi. And, for the sake of time right now, I'm going to try to streamline this, especially so we can make the video a bit shorter as well, and hopefully squeeze more in. But suffice it to say, by using the calculator, I'm not going to take the time to type this all in on the 89. I'll trust that you guys can do that on your own, and it wouldn't be that difficult, I hope, to see that we would get 4 pi over 3, and I'm going to say via calculator. Okay, just trying to streamline the lesson a little bit. On tonight's homework, you may use your calculator extensively. I'm not trying to say that some of the problems aren't easy to do by hand, but let's be honest, it can be a lot of setup as well. So let's very quickly go to the next page. Applications. Surface area has many applications as well. We could say that we've got a thin sheet, perhaps like a lamina, aluminum foil. It could have a surface, maybe the surface of a sphere or something else. By the way, those of you studying electricity and magnetism, you'll be dealing with problems like that soon enough. And perhaps you've even dealt with seeing problems in physics where you might have a metal ball surface and so forth. But suffice it to say, you could find the mass of the sheet. If you have a density function, you could have the center of mass. And notice we're using surface integrals to do this. By the way, I think we've got enough to deal with for our final exam. I'm not going to put in center of mass and a density problem like that. It's just suffice it to say that there are applications. I think we've got plenty other things to worry about. Well, in any event, let's keep going. For any surface S, you might say, okay, well, that's all well and good if we've got spherical coordinates or if we've got, a problem where maybe polars can be directly applied. But let's be honest, most of the time we're dealing more specifically with a z equals some equation, like z equals x squared plus y squared or something like that. And here we go again. I said earlier in the week that parametrically what you can do is you could say let x equal x, let y equal y, and then z would simply be that function that we've defined, whether it's x squared plus y squared or whatever. Z is that function g of x comma y. So we've dealt with this before. Imagine that this is written out in a kind of a other format. We did this last time as well in this last section. So lots of review. I'll tell you, for the sake of time, I'm not going to rigorously work out and reprove what we did yesterday. But suffice it to say that you could take derivatives of r with respect to x and y. You could take their cross product. We did that yesterday, and we found this to be true. You see that so very often that it's worth memorizing that r sub x, the partial derivative of r with respect to x, cross-producted, with the partial derivative with respect to y, it's opposite partial g with respect to xi minus partial derivative of g with respect to yj plus k. And then if we took the length of that, the norm, of course, we would just get the Pythagorean theorem. We saw that yesterday as well. Here it is showing up again. So sometimes kids are like, so why are we revisiting this? Well, now it's new, though it is a surface integral. Look at that s there. You've got a function out in front. This function is different than g. It's different than g, of course. It's going to be the function that you're evaluating the surface over for any point on that surface. So you're going to be dealing with some surface equation, but they're going to give you another problem to work out as well. We're going to see that in just a moment. Another function to be evaluated. So one other comment, similar formulas apply when it's more convenient to project S onto a different plane. Who's to say that your equation is z equals x squared plus y squared? Maybe it's y equals x squared plus z squared. You could have a paraboloid that's opening about a different axis, is what the author is saying right here. And if that's the case, you could very quickly make some appropriate adjustments, and you would see, for example, if y was a function of x and z, you might guess what's going to happen. You can see inside that length of the cross-producted vector, you can see we'll have a partial derivative with respect to x squared, a partial derivative with respect to z squared, because that's what our function y is based off of. And then we'd always have a plus 1. So that's something to keep in mind. Let's do a problem together and see how it plays out. We've got example 2. And they're saying, hey, work this surface integral out. The function that you are given in the integrand here is y. But the surface is, of course, very different, isn't it? And that's why I was saying before, you're going to be dealing with, of course, this twofold kind of an issue. You've got the surface, but remember, we're evaluating a function on little patches of that. We're going to take those little area patches and multiply that to a function evaluated at a random point there. So what we could see immediately following this box of number 4, following that, we know we're going to need to take a partial derivative of z with respect to x. What would that be? If z is equal to x plus y squared, we'd get what? Just a 1. And how about a partial derivative of z with respect to y? What would that be? 2y. Well, according to what we're seeing right here, we're going to use this box right here and say we're going to integrate over a domain. By the way, they're telling us the domain at the very end. That's going to be helpful. Here's our function out in front. Well, what is that function? It's y. And then I'm going to say, well, now I need the partial derivative of z with respect to x squared. That's 1, quantity squared, plus, then we're going to take the partial derivative of z with respect to y, which is 2y, square that, finally say plus 1. And we're getting there. We're so very, very close to wrapping this up. We could say inside this radical we've got 1 plus 4y squared plus 1, and then we could have a dx and a dy. And our dx, if you think about it, that will be integrated between 0 and 1. With y, we're going to integrate between 0 and 2. So all of this is going to be working out to this. Now again, you can use your calculator to work this out. And again, just trying to streamline this, trying to make this as quick of a process as we could. And you could certainly even work this out with some u substitutions. Don't get me wrong, some of these integrals really aren't so bad. You'd find that this would become 13 root 2 all over 3. So that's what this surface integral would work out to. Okay, so I'd leave that to you to confirm that the double integral would work out to be of that form. Okay, so we're gonna have to wrap up the video at this point and have to have a second part to it.